Okay, so in today's video we're gonna talk about Euler's number, and our comparative question is: throughout the history of mathematics, a compelling concept and a mathematical constant emerge, particularly in calculus and exponential functions, and is often denoted as E. Specifically, it's a base of the natural logarithm. So where does this concept come from? How does it work? And how does this apply to the real world? So it was first begun in the year 1683. This guy named Jacob Bernoulli studied a problem involved compound interest, so money compounding over time, basically. He analyzed an expression, and we're gonna take a look at the expression in a moment. So this expression calculates how much money grows when interest is compounded a number of times per year. He discovered that as the number approaches infinity, this expression approaches a fixed limit, which is slightly above 2.7. Okay, so this is the expression he was talking about, and we're gonna look over detail what's going on here. So let's say you put $1 into a bank, and that bank has an interest rate of 100%, which is like crazy. You're gonna become a billionaire by the end of, I don't know, 60 years or something. Yeah. So the first year your money will double. So you put $1, it'll return you to a total of $2 by the end of the year. But let's say we do that every 6 months. So every 6 months you get 50% of interest, and another 6 months another 50%. So this is what happened. This dollar after 6 months it become $1.50, and after that another 6 months it will actually turn into $2.25. But how about every month? And right now we see this expression being used. So basically this is a dollar you put in, this plus the interest, like the amount you earn in interest, and that number will be raised to about 2. So that'll give you a total of $2.613035 by the end of the year. So let's actually keep going. What about every week's compounding interest every week? So that'll give you a total number of 2.69, and this is every year. So that'll give us 2.71, and if you recognize the pattern, the number will increase over time, and later on when we do larger number than 365, we see this number approaches like slightly above 2.7. So Jacob Bernoulli, he didn't actually like work it out. He didn't put the number to like a billion or something. So he only knows that the number is above 2.7. Okay. But then, a few decades later, in the early 1700s, this guy Leonhard Euler explored this theorem constant further. So, around 1727 to 1731, Euler, he was the first person to use a simple E to represent this number. He discovered that E could also be defined by infinite series. So basically, what he's saying is, Jacob, he didn't work it out to this number being like goes to infinite. He only knows this number will reach like above 2.7. But this guy, he took another step beyond that, and he actually calculate further on the value of the number and give it a name, which is E. And this is all the expression, and this is all the equations that are equal to E. We'll be focusing on these two in today's video. So basically, if you take a look at this, we got the first original thing, no, but look at this. In math, it's called limit. So basically, what it's telling us, like, replace the n to infinity. Like, just imagine it's raised to the infinity, and you get E. The further the n is, the longer the E is equal to. So E is approximately equal to 2.718288.182854523 I believe, and so on. This goes on forever. And you see this, like, I put it in decimal, when I raise it to 1 billion, the number is like 2.71828. So yeah, this number matches the beginning of the digits. The rest is not, because this number is not infinity. But so Euler's number is used in calculus, probability statistic, complex number, and natural growth model, and it has a very unique property. We'll see it in a second. Okay. So there's gonna be two things we're gonna talk about. So first, you have to understand about exponential functions. There's two things you wanna know about. The first, that exponential function, they grow very, very fast. So if you look at this slide, I don't know if you can able to see it. I say it just goes from here straight up and just go on forever. And the second thing is a derivative. The derivative is basically it's rate of change in a function. It's basically how fast something is changing. It's a rate of change. So in this image depicts that the green line is a derivative of 2x. The rate of change of the function 2 to the power of x is actually like slightly smaller than 2 to the power of x. Okay, next. And for another function, exponential function, which is 3 to the power of x, here you can see the function. This is a derivative of 3 to the power of x, the purple line. The rate of change is actually slightly above 3 to the power of x. However, there is an interesting exception to consider. I invite you to examine these two graphs. Initially, you may perceive them as representing two distinct functions, but what if I were to tell you that there is, in fact, a single function whose derivative is equal to the function itself? You might have already guessed which function I'm referring to. It's e to the power of x. There are no other exponential functions whose derivative is equal to the function itself. The fact is essential in calculus, physics, and differential equations. Ultimately, it has given rise to one of the most beautiful mathematical equations ever. Welcome to Euler's identity. You may have already encountered this remarkable equation before. Many consider it's the most beautiful mathematical equation because it encompasses 5 fundamental mathematical constants. It involves e being raised to the power of I, the imaginary unit, which representing the square root of -1, multiplied by pi. It's the ratio of a circle's circumference to its diameter. When you add 1 to the entire expression, you arrive at 0. So, however, what does this all mean? How can you have an irrational number being raised to an imaginary number times another irrational number? And that's where I present you Euler's formula. Euler's identity is derived from Euler's formula, which states that e to the I theta is equal to the cosine of theta plus I times sine theta. However, Euler's identity is merely a special case of this formula. To illustrate this, consider the following table where e to the I theta is expressed using different values by substituting these values, we obtain the result shown. And you can also verify this using decimal. So by substitute this value of theta with pi, we arrive at -1, which is known as Euler's identity. Furthermore, it's fascinating to note that Euler's formula describes a circle, as illustrated by in the accompanying image. But why is this the case? Why did this exponential function result in a circular path? Wasn't it expected to increase? To grasp this concept, we should break down the equation using the Taylor series expansion, examining it in finer detail and combining the components systematically. This process involves calculating the sum of x raised to the power of n divided by n factorial, where n ranges from 0 all the way to infinity. For example, when evaluating e raised to the power of 1, we obtain 2.718281828 and so on. This illustrates the justification for the Taylor series. Now let's take a step further. Instead of e raised to the power of 1 or x, we will consider e raised to I times theta. This will lead us to a different expression. This expression arises when e is raised to I times theta. We begin with 1 plus I theta plus I theta to the power of 2 divided by 2 factorial plus I times theta to the power of 3 divided by 3 factorial and so on. However, when substituting I with its exponential forms means you arrive at a new expression. Interestingly, this latest expression features alternating values. Observe the size. This transition from positive to a positive, then to a negative, and then to a negative, with the pattern repeating itself. So it's gonna be positive, positive, negative, negative, positive, positive, negative, negative, and so on forever. Okay. And this related to our previous discussion about circles. Well, we also see noted a sequence of 2 positive followed by 2 negatives and the pattern persisting similarly. You see a positive, and then to a positive, to a negative, then to a negative, and then this repeats itself. Okay, next. So here's my drawing, and consider what occurs when we take out the I terms from this expression. So take out this term with the I, then stick into it, and we're left with the Taylor series of expansion for the sine and cosine functions, as illustrated as a company image. And you can also pause the video to take a closer look. Anyway, by applying substitution, we find that I to the I theta is equal to the cosine of theta plus I times sine theta. So yeah, which is known as Euler's formula. So yeah, that's where Euler's formula come from. Using the Taylor series of expansion to break this down, and you get this. And you take out the I terms, and the rest is equal to cosine. All the items is equal to sine, which add together, you get this whole thing. Okay, next. Here's some key takeaway. Euler's number, a vital mathematical constant, plays a crucial role in understanding growth and change. Its origins trace back to Jacob Bernoulli, who discovered it while calculating continuous bounded interest. Euler's number is fundamental in various fields such as calculus, finance, physics, probability theory, and differential equations. Notably, the derivative of e to the power of x is equal to the function itself, making it unique among functions as its rate of change is identical to its value. Lastly, there is much more to explore about this number, and I encourage you to delve deeper into this fascinating concept beyond what I can cover in a single video. Thank you.